Alright guys, welcome to Graphing Quadratic Functions, and today we're going to talk about standard form for graphing. So we're going to talk about standard form, factored form, and vertex form, but today is just all standard form. So there's three ways where you can really graph quadratic functions. Okay, so you can see in the picture here, a quadratic function is the first function we look at that's nonlinear, okay? And it's got this U-shaped, and we call the graph of any quadratic function a parabola. It's parabolic in shape. So this is the parent function of y equals x squared, okay? And the parent function is the simplest function in any family that hasn't been manipulated, stretched or shrink, lifted up and down, moved left and right, okay? So a couple of key things here. The vertex is the point at which the function changes direction, okay? And then the axis of symmetry divides the parabola into mirror images. So if you think about an axis of symmetry, you think of a line going right down the middle of your face. It's a mirror image on both sides. And that's what the axis of symmetry is. And so we're going to talk about that today. And I got to give a shout out to Rebecca, who helped me with this table. So the handwriting's a little different. One of our students helped us create these boards today. Okay, so in the first couple of examples here, we're just going to be looking at the value of a. Now in class we discussed and did an activity on how a affects the parabola. So, and we're going to graph this function, and how does this compare to y equals x squared? So when you look at this right now, we know that a is increased from 1 to 2. So how this is going to compare to y equals x squared? This graph is going to be more narrow, okay? It's still going to open up because a is positive. Now, since I don't have a b value and I don't have a c value, since the b value is 0, okay, and the c value is not there, I know that the origin is going to be the vertex, okay? So when you have a quadratic with no b term and no c term, an easy way to graph this function is to create a table of values. And so that we did here in step number 1. Now, a good rule of thumb when you're graphing functions, going from -2 to 2 for your x values is really good. Okay, so what we do here is every x value gets plugged into 2x squared. When you plug 0 in, you get 0. When you plug 1 in, you get 2 times 1, which is 2. 2 squared is 4 times 2 is 8. And also -2 is 8. So when we talk about that mirror image, let's plot these points. So we plot all of our points here. And Rebecca didn't make tick marks, but that's okay. So here's 1, 2, and 2, 8, -1, 2, -2, 8. Okay? They're mirror images. We're the same distance from here to the axis of symmetry as this point is from the axis of symmetry. And so that's what we mean by mirror image. Same distance from the axis of symmetry, or the same distance from the vertex. Okay, so part number 1, we create the table of values. Part number 2, you plot the points from this step. And number 3, you connect the points with a smooth line. Don't go down and then up. It's just a continuous smooth curve. Okay? In the second example, we're going to graph y equals -1/2 x squared plus 3. Okay? So, here's what's going to happen. We're going to create a table of values. Okay, now notice how the a value is -1/2. So there's two things. The function is going to open down because a is negative. And step number 2, the a value, the absolute value of that is between 0 and 1. So this graph is going to be wider than the parent function y equals x squared. So we're going to create the table. Now, again, the b value is 0. Okay, so the axis of symmetry is going to be, again, at the origin. Okay, and we're going to get into more talking about the axis of symmetry in the next couple of examples, how to find it. But again, if there's no b term, the axis of symmetry is going to be through the origin. There is a c term here, so we shifted the graph up 3 units. So when we create our table, notice how we didn't go from -2 to 2 this time. Look at the a value. That a value is -1/2. So I wanted to pick x values that were multiples of 2, so when I simplified, I got something easy to work with. Now 0 is nice because when you plug 0 in for x, you get 0 plus 3, which is 3. There's our first point. You plug 2 in, 2 squared is 4. -1/2 of 4 is -2 plus 3 is 1. And that's the same thing here for -2. These numbers are both the same distance from 0, which is where that axis of symmetry should be. So their outputs should be the same, and the same thing if for 4 and negative 4. Because there's no b value, the axis of symmetry is 0, and the line x equals 0. So if we're the same distance to the right, like 2 units from that axis of symmetry, and we get 1, that means negative 2 units to the left of this axis of symmetry, which should also be 1 on the output. So that's why you keep seeing these repeated values, both that are the same distance from the axis of symmetry away, and both are going to give you the same result. So I created my table, I plug each value in, and I connect them with a smooth curve. The function is opening down, which is a good thing because my a value is negative. Now here are some characteristics of y equals ax squared plus bx plus c. And in the next couple slides we're going to actually graph when we have a b value and a c value. We learned a lot of these in class. When the absolute value of a is greater than 1, the graph is more narrow. When the absolute value is less than 1 and greater than 0, so it's between 0 and 1, if that absolute value is between 0 and 1 for a, your graph widens. If a is negative, the parabola opens down. If a is greater than 0 or positive, the parabola opens up. C is the y-intercept, and here's the big thing. The axis of symmetry is the equation x equals negative b over 2 times a. And that b and that a value come from your function up here. So let's look at a couple more. All right, so in this example, we're going to graph 2x squared minus 8x plus 6. So again, number one, you're going to want to identify your variables. See what's going on here. A is 2, so the parabola is going to open up, and it's going to be wider because, or more narrow, because that a value is greater than 1. So 0, 6 is the y-intercept. Okay, there's your c value. That's another thing. AOS is the axis of symmetry. So we know that in this case b equals negative 8, a equals 2. And so I'm going to plug them into the opposite of b over 2 times a. Well, the opposite of negative 8 is 8. 8 divided by 4 is 2. So the line x equals 2 is my axis of symmetry, and I've drawn that here in red. So we go over to 1, 2. There's the axis of symmetry. Now, the axis of symmetry always goes through the vertex. The vertex has a coordinate. We're going to learn they're called h and k. Okay, but the vertex has the x coordinate that's equal to the axis of symmetry, and that's always the case. The vertex will always go through the axis of symmetry. So if I have my axis of symmetry being 2, my vertex should be 2, comma, in this case, negative 2. So how do I do that? I have my axis of symmetry, which is 2. The x coordinate of my vertex is 2. To find that y coordinate, we plug 2 back into the original function, which is what we've done here, and we get an output of negative 2. So let's look at the graph. So we're at 2, and we go down to negative 2. There's our vertex. The third step, which isn't shown, is we plug a couple values in to evaluate and see where we can plot extra points. I always try to choose points that are one to the right and to the left of my axis of symmetry. So if I plug in 1, okay, we'll get rid of that. So we have 1, and we plug in 1 for x. We get 2 minus 8, which is negative 6, plus 6 is 0. So I plot 1, 0, and that's where I see Rebecca wrote that. Now, if I'm 1 unit away from the axis of symmetry and at 0 to the left, if I move 1 unit to the right, I should also be at 0 because they're the same distance from the axis of symmetry. So I plot this point and I draw a smooth curve for my graph. In the last example, sorry Rebecca, she bailed on me for the last example. So we're going to graph our standard form x squared minus 2x minus 1. So a couple things. The a value is 1. The parabola opens up. The y-intercept is 0, negative 1. The axis of symmetry is the opposite of b over 2a. b is negative 2, a is 1. So I substitute in, and I get my vertical line at x equals 1. So notice at x equals 1, there's my dotted axis of symmetry. Okay? Now, when I get the axis of symmetry, I also get the x-coordinate of my vertex. To get the y-coordinate, I plug in that 1 into my original function, and I get -2. So the vertex is 1, -2. So we look at 1 and -2 and we plot. Now, in the last example, I picked some x values and plugged them into our original function to get some more points for my parabola. But in this case, I know that the y-intercept is 0, 1. It's something manageable. So I plot 0, 1. And since the vertex is at 1, we're 1 unit away from the axis of symmetry, and we plotted 0, 1. So if we go to the right 1 unit, we should be at -1 as well, because this is a mirror image on both sides. So I plot 0, -1. 0 is 1 unit away from the axis of symmetry, so then I move to the right of the axis of symmetry 1 unit and plot the same output value. And that's what that symmetric means. Symmetry means with that axis of symmetry. Plot a smooth curve here, and we're all set. So that's graphing parabolas in standard form. And what we're going to do next time is look at parabolas in vertex form, and we'll learn that vertex form shows you a little bit different things. Same smooth curve, but it's going to tell us something different. Standard form here is nice because it gives us the y-intercept right away, and we've got the values that can help us get to the vertex, but it doesn't give us the vertex right away. So if you have any questions or comments, you can type them below. You can also email me at nicholas.bennett@dc.gov. Thanks.